So resonance is defined as a structure that has more than one form. So you can have a structural form that is A form, B form, and C form, and the A, B form, and C form are all equivalent. That is to say, not one form is favored over the other form. So resonance means you can have more than one structure, and they are equally favored. So the best example of resonance structure would be the nitrate ion, and there's more than one correct resonance Lewis structure form of the nitrate ion. So let's draw this here. So nitrogen, as we know, is happy at 5. Oxygen is happy at 6, but we have 3 of them, so that's 18. And that minus sign implies that we gained an electron. So 5 plus 18 plus 1 is 24. So our goal here is to try to figure out how to get 24 valence electrons around the nitrate polyatomic ion. This is actually one of our first molecules that we did our flashcards under. So let's make nitrogen our central atom because we don't know which of the 3 oxygens is going to be central. So we'll make this very simple and have nitrogen as the central atom. And then we're going to bond 3 oxygens to it. Okay, so 1, 2, 3. We need to get 24 valence electrons in there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, so something doesn't look right here. One thing is we have a negative, -1 charge on the whole nitrate ion. Calculating the formal charge on just one of the oxygens, let's do that here, and we will see that formal charge 1, 2, 3, 4, 5, 6, 7. Oxygen is happy at 6. 6 minus 7 is -1. Well, we have a formal charge of -1 here, but it's also going to be -1 here, formal charge, and a -1 there, formal charge as well. So that's not very good. Let's look at this nitrogen here, formal charge. Okay, we got our 24 valence electrons, but the arrangement of the configuration is a little bit off. Okay, it's off key here. So formal charge on this central nitrogen atom, 1, 2, 3, 4, 5. Nitrogen happy at 5. 5 minus 5 is 0. So this whole thing has a charge of -3. Nitrate ion has a charge of -1. So the easy way to remedy this, and this with practice you can see it, I'm going to make a double bond here. And actually, if I make a double bond here, that's going to remove that, giving us a -2. I need a -1, right? So I'm going to make another double bond here. And when I have a double bond there, moving this pair of electrons here, I have my -1. So let's redraw this. Okay, so we're going to redraw this situation, creating double bonds. Okay, so we have a double bond here at the top. Okay, here's our 2 lone pairs. Okay, on the left-hand side, we also make a double bond, and these are our 2 lone pairs. Here on the right-hand oxygen, the rightmost oxygen, I left it alone, so I'm going to keep that formal charge alone as minus. Okay, and so remember, we need 24 valence electrons. So let's just make sure we have 24. I'm pretty sure we still have 24. We really didn't change anything, but let's just count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So our 24 valence electrons are all accounted for. And let's look at the formal charge. The formal charge of this oxygen that's double bonded. 1, 2, 3, 4, 5, 6. Oxygen happy at 6. 6 minus 6 is 0. The octet rule for this oxygen that's double bonded. 1, 2, 3, 4, 5, 6, 7, 8. So the octet rule is good. It's going to be the same thing for this oxygen up top because they're both double bonded to the nitrogen. And this oxygen we already know is a formal charge. This nitrogen formal charge, okay, 1, 2, 3, 4, 5. Nitrogen happy at 5. 5 minus 5 is 0. The formal charge looks really good on that nitrogen. The only issue is that we have an expanded octet, which is fine. Okay, it's okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So instead of 8, we have the expanded version, the expanded octet for the nitrate ion NO3 minus. So this is good. This is a representation of the nitrate ion, but that's not the correct answer. In fact, it's 1/3 of the correct answer. The reason why I'm saying it's 1/3 of the correct answer is because of resonance. Okay, so there is 3 forms of the nitrate ion. All of them are equally weighted. All of them are equally valid. And it has to do with the location of the single bond. So I put a double bond here and here, okay, by moving, let's move this above. I move this pair of electrons there. I move that pair of electrons there. But that's rather arbitrary on my part. You see, I can move this pair of electrons here and move that pair of electrons there and have the double bonds left and right. Okay, I can have the double bonds top and right. Okay, so here I chose to have the double bonds top and left, but there's also other arrangements of the double bond. Okay, so that is what resonance is. So I drew one form. Okay, let's draw the other two. Here in this form, I have the single bond on the this side, which is the right-hand side. So let's make it on the top-hand side, shall we? So in order to make the double bond or the single bond on the top-hand side, I'm going to move this pair of electrons here, and I'm going to move that pair of electrons, kick it out back up top. So, okay, so this is equivalent to this form with the N, the single bond oxygen. Okay, now it has 3 lone pairs. Now this has the minus formal charge. Okay, remember, it has this, the minus formal charge. The minus formal charge now goes up top. By kicking those electrons, I create a double bond on the rightmost oxygen. The formal charge here is now 0. And the left-hand oxygen substituent, I really didn't do much. I didn't mess with it. Okay, so that's one form of nitrate. And then my final form of nitrate is where I'll kick out this pair of electrons. Here on the rightmost side, I'll make a double bond there. And now my single bond is on the my single bond is on the leftmost oxygen. I have a double bond now. Instead of top and left and right, I'm going to have my double bond top and right. In other words, the single bond has interchanged and is delocalized amongst the 3 oxygens. So let's draw this final rendering of our resonance structure. So we'll have a double bond here. Okay, the formal charge now. Okay, the formal charge now is on this oxygen, and I really didn't change anything here. So that is the resonance structure of the 3 resonance structures of the nitrate ion. All right, so let's get our highlighter here and recognize that the minus formal charge of the nitrate, okay, in this form, it was located on this oxygen atom. In this resonance form, it was located on the top oxygen atom. In this form, it's located on the the leftmost oxygen atom. So notice the minus sign has delocalized. Okay, so that's a key point in resonance structures. They're exceptionally stable because the minus sign is shared equally amongst the electronegative oxygen atom. We call that delocalization. So it buzzes here, and then it buzzes to here, and then it buzzes here, just buzzes all around like a bee. So that negative, full bear and brunt of that negative charge is equally delocalized across all 3 oxygen atoms. Notice the single bond arrangements. I'll highlight them. Single bond to this oxygen, single bond to that oxygen, single bond to that oxygen. Notice the double bond configuration, top and left and right, top and right. Resonance. Hybrid structures, all of them are equal. All of them are the same, and all of them are the correct answers to the question, what is the resonance structure of the nitrate ion?